Microsoft made a promise in 2021, not in the quiet technical language of a security bulletin, a public promise, a hard line drawn in the sand. If your computer didn't have a specific chip on its motherboard, it could not run the new version of Windows. No exceptions. No workarounds they officially endorsed. No grace period for older machines. The chip was called a Trusted Platform Module, version 2.0, TPM 2.0. And the message from Microsoft was unambiguous. This chip is so important to security that hundreds of millions of existing PCs are simply not good enough without it. The requirement was controversial. It was loud. It forced people to throw away machines that otherwise ran perfectly. It accelerated hardware refresh cycles across the entire industry. And it was, Microsoft insisted, worth all of that disruption. Because the TPM was the foundation, the bedrock, the hardware root of trust that everything else in the new, more secure Windows would be built upon. That chip just failed. Twice, actually. In 2023, researchers found a pair of buffer overflow vulnerabilities in the TPM 2.0 specification itself. And now in 2026, 2 more high-severity flaws have surfaced, this time capable of something even more unsettling than the original pair. These new vulnerabilities don't just threaten your data, they threaten the chip's ability to tell the truth. So the question is unavoidable. What does it mean when the foundation has cracks? To understand what's at stake, you need to understand what TPM 2.0 was supposed to do. And that means understanding the problem Microsoft was trying to solve. For years, Windows ran on essentially anything. Old hardware, cheap hardware, hardware without any dedicated security components at all. This was part of Windows' appeal. Universal compatibility, the operating system that would run on whatever you had. But that flexibility came with a cost. Without dedicated hardware to protect the boot process, Windows was vulnerable to a class of attacks that are particularly difficult to defend against. Attacks that happen before the operating system even loads. Rootkits, firmware-level malware. Bootkit infections that embed themselves so deeply into a machine that even a full reinstall of Windows can't remove them, because by the time Windows starts, the attack is already in control. The TPM 2.0 chip was designed to solve this at the hardware level. The chip sits on the motherboard, separate from the main processor, with its own isolated memory and its own cryptographic engine. When the PC turns on, before Windows loads, the TPM takes measurements. It generates a kind of cryptographic fingerprint of the boot chain, the firmware, the bootloader, the early components of the operating system. It compares those measurements against known good values. If anything has been tampered with, the TPM knows. This process is called measured boot, and it's just one piece of what the TPM provides. BitLocker, Microsoft's full disk encryption tool, uses the TPM to seal its encryption keys. Which means if someone steals your laptop and tries to boot the drive in a different machine, the TPM that generated those keys isn't there anymore, and the data stays locked. Windows. Hello, the passwordless face recognition and fingerprint system, uses the TPM to store credentials in hardware rather than in software where they could potentially be extracted. Credential Guard, a feature that protects login tokens from malware, uses the TPM to anchor its security. The whole architecture of modern Windows security pointed back to one thing: the chip. And if the chip couldn't be trusted, the architecture built on top of it had a problem. When Windows 11 arrived in October 2021, the TPM 2.0 requirement hit like a wall. The backlash was immediate and substantial. Forums flooded with frustration. Tech journalists wrote explainers. YouTube filled with tutorials on how to bypass the check. Estimates suggested that hundreds of millions of perfectly functional PCs were now considered incompatible. Not because they were slow, not because they lacked RAM, not because they couldn't run the software, but because they were missing a chip that most consumers had never heard of. Microsoft didn't back down. If anything, the company doubled down, publishing blog posts explaining why TPM 2.0 was essential, why it wasn't negotiable, why the security gains justified the disruption. The message was consistent. This is the future of PC security, and the future requires hardware that can support it. There was a legitimate case to be made for that argument. The threats TPM 2.0 addresses are real. Firmware attacks and bootkits are serious, sophisticated threats that software-only defenses struggle against. Hardware attestation, the ability to cryptographically verify that a device is what it claims to be, is increasingly important as organizations build security models around device identity rather than just passwords. But the premise underneath all of it was that the chip itself could be trusted. That premise was about to be tested. In March 2023, a pair of security researchers at a firm called Quarks Lab published the results of a vulnerability investigation. They had been looking at the TPM 2.0 reference implementation, the codebase that describes, in precise technical detail, how a TPM 2.0 chip should behave. The reference implementation is published by the Trusted Computing Group, the nonprofit consortium that develops and maintains the TPM specification. When chip manufacturers build their TPMs, they work from this reference. What the Quarks Lab researchers found were two buffer overflow vulnerabilities in that reference code. The bugs were tracked as CVE 2023-1017 and CVE 2023-1018, an out-of-bounds write and an out-of-bounds read, both occurring in the same routine that handles encrypted command parameters. The mechanics were specific. When the TPM processes certain commands with encrypted parameters, the code could be tricked into reading or writing 2 bytes past the end of a memory buffer. 2 bytes doesn't sound like much, but in cryptographic hardware, 2 bytes in the wrong place can be catastrophic. Depending on what occupied that memory location in a given manufacturer's implementation, the consequences range from crashing the TPM entirely to potentially executing arbitrary code within the chip's protected environment. The CERT Coordination Center issued a public alert. The Trusted Computing Group acknowledged the flaws and published fixes. The security community absorbed the news and moved on, as it usually does. But the story had revealed something important. The reference implementation, the shared foundation that countless TPM products are built from, could carry bugs, not hypothetical bugs. Verified, reproducible, CVE-assigned bugs in the specification level code that was supposed to define what a trusted chip looks like. The chip's trustworthiness was not guaranteed by its purpose or its name. It was guaranteed by its code. And code has vulnerabilities. Now we arrive at August 2026, and the story has a second chapter. This time, the vulnerabilities are different in nature, and in some ways, more philosophically troubling than the first pair. 2 new flaws were disclosed simultaneously by the Trusted Computing Group, AMD, and Carnegie Mellon's CERT Coordination Center. The CVE numbers are 2026-6726 and 2026-6727. The CVSS severity scores are 8.5 and 8.3, both rated high. Intel researchers discovered the bugs and reported them through responsible disclosure channels, with patches available from AMD and through BIOS updates before the public announcement. The first vulnerability, CVE 2026-6726, is rooted in how the TPM reference code separates different types of objects in memory, key objects. The cryptographic keys that TPM protects and hash context objects are supposed to be stored separately, with clear boundaries between them. The bug is that this separation is insufficient. An attacker with privileged local access can manipulate object slots in a way that the TPM does not correctly invalidate keys that have been discarded. A new falsified key can occupy the same memory address as a genuine one, and the TPM's verification routine can be fooled into treating the fake as real. The consequence is not just data theft. The consequence is impersonation. With a forged attestation key, an attacker can present a compromised machine to a certificate authority and obtain legitimate credentials for a fake TPM identity. A device that has been tampered with, one that should fail any legitimate integrity check, can instead pass, not by fixing the tampering, by making the hardware root of trust lie. The second vulnerability, CVE 2026-6727, operates differently but leads to related damage. It is a timing side channel in the TPM's implementation of RSA OAEP decryption. Timing side channels are a classic and uncomfortable class of cryptographic attack. The algorithm doesn't leak the secret directly, but the time it takes to run the algorithm varies depending on the secret's value. By sending carefully crafted commands to the TPM repeatedly and measuring how long the responses take, an attacker can use those timing differences to recover information about encrypted data, including, potentially, the keys the TPM was protecting. Both vulnerabilities require privileged local access. An attacker needs to already have elevated access to the machine to exploit them. That requirement meaningfully limits the risk for most ordinary users on ordinary home machines, but privileged local access describes exactly the position an attacker reaches after an initial compromise, after a piece of malware has run, after a phishing attack has worked, after a supply chain intrusion has succeeded, and it describes the situation of an employee with a company laptop who is not who they claim to be. In enterprise environments, in zero-trust security architectures, in remote work deployments where identity verification happens through device attestation, this is precisely where the consequences get serious. Let's be direct about what attestation is, because it's the concept at the center of this story. The whole enterprise security model that has been built over the past several years rests on a principle called zero trust. The idea is that you never automatically trust anything on your network just because it's there. Not a laptop, not a server, not a device claiming to be managed and compliant. Everything has to prove what it is before it gets access to sensitive resources. The TPM is how that proof works for a PC. The chip generates attestation data, a cryptographic statement that says, this is the specific device with this specific configuration in this specific state. Because the statement is generated inside tamper-resistant hardware, and because the hardware holds keys that were issued specifically to that device, the statement can be verified. The device can prove it is what it claims to be. Zero trust security doesn't work if attestations can be forged. If a compromised machine can present a valid attestation, if the hardware root of trust can be manipulated into signing a lie, then the security model built on top of it collapses at the moment it matters most. Not when the device is healthy and compliant, when the attestation is accurate anyway. At the moment when the device has been compromised and should be denied access, when the attacker is already on the machine and needs to maintain a foothold, when the whole point of attestation is to catch exactly that situation. That is the scenario CVE 2026-6726 speaks to directly. AMD has confirmed that both vulnerabilities affect its firmware TPM implementation across an extensive range of processors, effectively the full span of its consumer and workstation desktop output since 2019, from Ryzen 3000 through Ryzen 9000, and including several Threadripper embedded in Ryzen AI series. Intel's firmware TPM is also affected by the underlying reference code flaws. The vulnerabilities were present in all revisions of the TCG reference code up through version 184, released in 2025. Firmware updates addressing both CVEs became available for most AMD processors in May 2026, delivered as BIOS updates from motherboard manufacturers. The responsible disclosure process worked correctly. The fixes existed before the public announcement. Users who have applied recent BIOS updates to their systems may already have the mitigations in place. But here's a practical reality that anyone who works in IT security knows well. The gap between a patch is available and a patch is applied is often measured in months, sometimes years. BIOS updates require deliberate action. They are not automatic. They are not installed by Windows Update. They require a user or administrator to go into their BIOS update utility, download new firmware, and apply it through a process that is more involved than clicking an update button. For enterprise fleets managing thousands of machines, this is a known workflow with tooling to support it. For individual home users with an AMD system built in the last 6 years, the question is, do they know this update exists? Do they know where to find it? Do they know what a firmware TPM is, or what CVE 2026-6726 means to their machine? For most of them, the answer to all three questions is no. This brings us back to the 2021 mandate and to the uncomfortable arithmetic it produces. Microsoft required TPM 2.0 for Windows 11. The argument was security. Hundreds of millions of PCs were declared obsolete, with users pushed toward new hardware that included the chip as a baseline requirement. The message, implicit and sometimes explicit, was that this chip represented a security guarantee, that having it meant your system had a foundation of hardware-backed protection that older machines simply couldn't provide. The chip was real. The security features it enables are real. BitLocker working with hardware-sealed keys is genuinely more secure than software-only encryption. Measured boot detecting tampered firmware is a genuine defense that has no direct software equivalent. Windows Hello, backed by TPM-protected credentials, is meaningfully harder to defeat than passwords stored in software. None of that changes because the chip had bugs. Security features built on the TPM still provide real protection in the vast majority of scenarios most users will ever encounter. But the framing of the mandate, the absoluteness of it, the way it was communicated as a line between secure and insecure, was always a simplification. Security does not come from owning a chip. It comes from a chip that is correctly designed, correctly implemented, correctly deployed, correctly updated, and operating against adversaries who haven't yet found a way around it. The TPM is a component in a security model that, like every security model ever built, has vulnerabilities that researchers find over time, that adversaries probe over time, and that require maintenance over time. The chip is not the guarantee. The chip is the starting point. There is a broader pattern here that deserves a moment of attention. The history of security hardware is littered with trust anchors that turned out to have cracks. Dedicated security chips and trusted execution environments have been a consistent target for security researchers, precisely because they are positioned as roots of trust. And attacking the root is the most consequential attack available. Compromise the layer that everything else trusts, and you don't need to defeat the protections built on top of it. You make those protections irrelevant. The TPM is not unique in having been found vulnerable. Smart cards have had implementation bugs. Hardware security modules have had side channel vulnerabilities. Secure enclaves in major processors have had their own well-publicized research findings. The pattern is consistent. Hardware security components are designed by humans, implemented by humans, and specified by humans, which means they can contain the same categories of errors that software contains: memory handling bugs, timing vulnerabilities, logic errors in how edge cases are handled. What makes each of these findings significant is not that they prove hardware security is worthless. They don't. They prove that hardware security requires the same ongoing vigilance that software security requires: specification updates, reference implementation maintenance, coordinated disclosure processes, firmware update delivery, user and administrator awareness. The Trusted Computing Group maintains a vulnerability response process. The coordinated disclosure around the 2026 CVEs was handled correctly. Patches were developed and delivered before the public announcement. These are signs of a mature response process working as intended. But the existence of a good patch process does not eliminate the importance of applying the patches. And it does not change the fact that the security guarantee Microsoft communicated in 2021 was always more conditional than the marketing suggested. What should you actually do with this information? If you have a Windows 11 PC running on an AMD processor, check your motherboard manufacturer's website for BIOS updates and apply the latest available version. This is the concrete mitigation for CVE 2026-6726 and CVE 2026-6727. If you're on Intel, check for relevant microcode and firmware updates through your system manufacturer's support pages. Be clear-eyed about your threat model. For most home users, these vulnerabilities require a local attacker with elevated privileges to exploit, meaning someone who has already substantially compromised your machine. That is a serious situation, regardless of the TPM vulnerabilities. And the TPM flaws make it worse, but they are not the initial entry point. Your everyday risk from phishing, weak passwords, unpatched software, and social engineering remains far higher than the risk from a targeted TPM side-channel attack. For enterprises and organizations relying on TPM-based attestation for zero trust network access, endpoint verification, or managed device compliance, these vulnerabilities warrant more urgent attention, because the consequences of forged attestations at that scale are genuinely significant. Review your device management and patch deployment processes. Prioritize BIOS update rollouts. Verify that attestation chains are not being trusted for devices that haven't received the firmware fix. And hold this in mind as a general principle: security features that depend on firmware require firmware maintenance. The TPM is not a one-time installation that provides security forever. It is a component that, like every other component, has a life cycle. That life cycle includes vulnerabilities found by researchers, disclosed through coordinated processes, and addressed through updates that require deliberate action to deploy. Return to the promise Microsoft made in 2021. The chip was not optional. The chip was the price of entry. Hundreds of millions of PCs that didn't have it were left behind. The users who were told to upgrade, who bought new machines with TPM 2.0 chips on their motherboards, who accepted the disruption and the cost because Microsoft said this was the secure way forward, those users now have a chip on their motherboard that has been found twice in 3 years to contain high-severity vulnerabilities in the specification that defines what it's supposed to do. That's not an argument for abandoning hardware security. It's an argument for accuracy about what hardware security provides. The TPM 2.0 chip does make Windows 11 more secure than Windows 10 on machines without it. That is still true. The features it enables are real, and the defenses those features provide against real attack classes are genuine. But the chip is not a guarantee. It is a hardware component in a security architecture that requires the same continuous investment in vulnerability research, in specification maintenance, in firmware updates, and user awareness that every security system requires. The promise Microsoft made in 2021 was essentially that hardware would solve a class of problems that software couldn't, that by requiring a specific chip, a security boundary could be drawn that would hold. The chip that was supposed to hold that boundary just needed to be patched. In security, nothing is guaranteed. No chip, no algorithm, no architecture. The goal is never to build something invulnerable. The goal is to build something that makes attacks sufficiently difficult, that fails gracefully when they succeed, and that can be repaired quickly when flaws are found. By that measure, the TPM is doing what it was designed to do. The Trusted Computing Group found vulnerabilities, published advisories, and delivered fixes through a coordinated disclosure process that got patches out before attackers could use the information. AMD responded. Intel researchers helped find the bugs. The system worked. But the system working doesn't mean the marketing around it was honest. The next time a technology company tells you that a specific piece of hardware will make your computer fundamentally secure enough to obsolete hundreds of millions of otherwise working machines, remember this. Hardware roots of trust are roots. They are not ceilings. They are the starting point of a security architecture, not the end of it. They require maintenance. They require updates. They require the same skepticism, vigilance, and ongoing investment that every other layer of a security system demands. The chip was supposed to be the foundation you could build on. It turns out it's a foundation that also needs to be repaired. And no amount of mandatory upgrade cycles changes the fact that a foundation, however solid it seems on the day it's poured, has to be checked, and sometimes fixed, for as long as you're building on top of it.